Hello.
Yeah, that's
I'm a professional. Huh?
session of today, and we're going to hear about vector strata from Nejc.
Okay. Thank you very much. Thank you for organizer for giving me the opportunity to give a talk. Um, the upshot of this talk is we found some equations which are six-dimensional equations of minimal supergravity coupled to vector multiplets. We wanted to solve them, and we wanted non-trivial microstate geometries in this theory. Now, what we've done, and what usually what is done in superstrata, that you look for, that you start analyzing your CFT to give you clues of how to solve your equations. And this is exactly what will be the topic of this talk. So the talk is how to effectively solve a linear set of equations. I understand that this is a very technical. It's quite unfortunate that I'm the last one right before wine and cheese. And in the technical talks is always a kind of like a, you don't want to give too much details because then you alienate everyone apart from the specialist. You don't want to give too little details because the specialist won't have anything to do. So I'll try to do like, you know, the golden middle. So then in the end, nobody will be happy. So I'll start with some basic introduction. I'll try to motivate how to get perturbation, how to do a CFT analysis that will give you how to solve these equations. In a sense, what I'm doing is basically similar to exponentiation of a state that Stefan has been talking about in his last talk. And then I'm going to go to the technical part. I'm going to build this perturbation, and then I'm going to go solve the linear equations, a set of differential equations. I'm going to analyze some solution, and then I'm going to, in the last section, I'm going to show why solutions are quite important and why they might be interesting for some further research. Yes?
Since you mentioned, when you exponentiate, you need to check that the operator is not simply marginal, but is what is called exactly marginal. That means that in the OP of this operator with itself, there is not the operator itself. Okay. Is it obvious for any reason?
I don't know. This is, I think if you ask the...
Stefano, where is he? Disappeared. You know that I was asking this, but you, Emil, you should be able to answer.
So the simplest example of this is the half BPS vertex operators that Stefano discussed. And so there we have a one-to-one map between, so there's a construction of the geometry that goes back to Lunin and Matur, where you express the harmonic functions that appear. No, because all the vertex operators carry charges. So it just takes you to something with some other charge. But well, let me let you. Yes.
I'm fine with it. I'm fine with it. Okay. But okay, let me start with something that basically is one of the main takeaways of Anthony's talk. If you want to find a back reaction of a system, it's really hard. It's really hard to find, if you start with your, some space-time, you put in some matter fields. Usually it works in the probe limit. You let your stuff in, it doesn't perturb the background, it's all fine and dandy. But then as you start pumping in more and more fields, more and more particles, more and more energy, at some point your approximation will break down, and what will happen is that this space-time will get deformed into this weird tube, what I picked here. Why is this important? Well, if you believe that your black holes in a suitable theory will be basically resolved in some kind of fundamental degrees of freedom, then this is the kind of problem that you will be looking at. And I think we will hear even tomorrow more about this systems. And in fact, most of the talks in this conference will be in some way, shape, or form related to this question. But this is notoriously hard. If you work, for example, in GR, I know this isn't, this might not be the right theory for, if you have this full UV complete theory. But even if you look in GR, this requires you to solve some, for example, some stress energy tensor, and then you try to solve this. So this is a second order differential equation, which is really hard to solve. And usually to solve these equations, either you know what the solution is, or you impose some kind of symmetry, or you make a simplifying ansatz. And this will be exactly the same, exactly what I will do in this talk. What I will use is, in fact, ADS-CFT and supersymmetry. And so just a very short recap of ADS-CFT. It relates a gravitational theory to a non-gravitational theory on the boundary. You use the gravitational theory in ADS to a boundary CFT. And one of the main things that I'll use here is that bulk excitations can be related to states in the CFT. So we saw this today. We saw this today with Anthony, and we saw how even if you exponentiate these states, you get back-reactive geometry. For our purpose, the only thing, the starting point that we'll need is if you have empty ADS, this would be the vacuum state. And if you have some excitation, some linearized excitation around this background, you will have some simple CFT state in them. Some simple light CFT states in the CFT dual. One of the things that was also mentioned here is that ADS-CFT is a strong-weak duality. So in principle, it's really hard to relate these two quantities directly because the gravitational theory, so for example, if you have supergravity in the bulk, this will be related to a strongly coupled CFT in the dual field. Related to a weakly coupled CFT, you'll have to move in the moduli space. And one thing that you can relate is protected quantities, and one of these protected quantities, symmetry. This is exactly what we will look into today. So we will look at supersymmetric quantities, and we will match the spectrum at the free point in the moduli space to the supergravity point in the moduli space, and then we will use our equations of motion, our BPS equations of supergravity, to fully back-reacted geometry. So this will be our motivation or our way forward to this topic. I will in particular look at ADS-free CFT2. Now this is of importance because this is the near horizon limit of the D1, D5 system, as was talked about today. So I won't describe it in much more detail. But for example, it's also important because this is the near horizon limit of the Schrödinger-Vafa black hole. So by counting states in this ADS-CFT duality, for example, you might get some handle on what are the states in the Schrödinger-Vafa black hole. What will be important for my talk is, in fact, that the isometries of the background. So the near horizon limit of large n is ADS-free cross S3 cross T4. I will take the internal manifold to be T4 for concreteness, but I think it's also important here. It's also important that it's not K-free. But the important part here is that I will take the isometries of the background. So the isometries of the background then get mapped to the symmetries of the CFT. So for example, the isometries of ADS-free become the conformal symmetry. The isometries of S3 become the R symmetry, and associated to those will be indices A and A dot. This will be important later when I have some arguments why certain states are related to vectors. And the T4 symmetry is not actually become the symmetries of the algebra. And for us, it's important that A and A dot indices are related to the T4 symmetries. The algebra naturally separates into left and right sectors. These are the generators for the symmetries of the left sector. The right sectors will be the same, only with barred quantities. And again, what I will say, just to be specific here, we will analyze the spectrum of supersymmetric excitations at the free orbifold point, which does not have a good supergravity description. This is also something that Ben will talk about on Thursday, I think. And then we will relate it to supergravity excitation at the supergravity excitation far away in the moduli space. Just to concreteness, I will central charge of the theory. So our conformal field theory at large central charge. Okay. Just a few details about the CFT. The only thing that some of the things that will be important for my talk. If you have large n, the way that you can think of the CFT is you have a string budget of n, and then you start forming strands. You can form a strand of length 1, and then you put a state on this strand. So in this case, I put a bunch of strands on which I put the vacuum. The vacuum can only be a strand of length 1. But you can also join several strings of length 1 into one longer strand, which I denote here with length k. And then you put a different state on those. And if I take a state which has a bunch of vacua and then just a small amount of different states, that will be in the supergravity point. This will relate to just a small linear excitation around the ADS-free S3 vacuum. And as is usual, I will use the symmetries to classify the states, and in particular, I will use the L0 and J3 eigenvalues to specify the states. And for particular importance, here will be anti-Kähler primaries. Now, these are states which preserve some supersymmetry. In fact, those are 1/4 BPS states. Just as a sort of translational tool, in the previous talk by Stefano, these were called 1/2 BPS states. Just the difference is that 1/2 is related to the amount of symmetries that D1, D5 CFT preserves, or the ADS-free, because S3 preserves, whereas we take 1/4 as 1/4 of all the supersymmetries to type 2B, just a technical detail. Now we have anti-Kähler primaries. The only thing that you need to think about is that basically they're lowest weight states of, for example, of the SU2 and SL2R multiplets. So in principle, what you can do, these are the lowest symmetry states, and you get more states by acting with symmetry generators. Then you just basically use your standard Virasoro techniques or standard quantum mechanics to just generate more and more states. So in fact, what you're doing now is a spin plus string theory. And those states, the anti-Kähler primary states, have been categorized. We have 8 bosonic states, which we denote by A dot, and A dot B dot, and 8 fermionic states, which we won't consider, which won't be important for us now. Just some hand-wavy intuition. Whenever you have, remember that I said when you have A and A dot index, those are related to excitations along the S3. So whenever you have states like this, they will correspond to some excitations which have leg along the ADS3 cross S3, just hand-wavy arguments. Whereas indices which have A dot B dot are naturally polarized along the T4. And in particular, a specific combination of these A dot B dots is called the 0,0 strand. And this has been particularly important for all the superstrata constructions so far. So these are the states on which original superstrata supercharged superstrata have been considered before. And they are very particular because they sort of correspond to polarizations as the breeding mode of the T4. So they are sort of universal because the only thing they depend on the T4 is the volume form. So they are kind of universal along the T4 and K3. We will break that. We don't care anymore. Just as a slight reference point, these notations I have conveniently borrowed from a review from Masaki, but I also heavily borrowed from Stephen Avery's PhD thesis and a review by David Mendal and Badia. Okay, so these are the antichiral primary states. These are the lowest weight states. You create more and more states by acting with symmetry generators. Those are L-1s, which lift your H in this J0+, which lift your M index. But also you have supersymmetry generators G. And this lift you into a different multiplet. So if I want to have new bosonic states, what I can do is start with a antichiral primary. I can either act repeatedly with J0- or L-1, or I can act twice with the supersymmetry generators and then have a whole new multiplet of bosonic states. If I want to preserve supersymmetry, I only act on one sector. So I will leave the right sector completely as it is. This is completely, I don't care about it anymore. It's going to be always in an antichiral primary state. And so, for example, the motion rotation based on 0,0 antichiral primaries is given by this combination, schematically by this combination. And these, when you backreact these can be mapped, for example, to spectrum of ADS3 cross S3, coupled to tensor multiplets. And once you backreact them, these give you the superstrata. And these were the original superstrata that people have considered before. Okay, what's the new thing? You can generate bosonic states by starting with fermionic states and then acting once with the supersymmetry generators. Remember, when you have supersymmetry, starting with a bosonic state, and with a supersymmetry generator, you get the fermionic state. Acting another time, you get a bosonic state. And when you start with the fermionic antichiral primary, acting once, you get a whole new set of bosonic states in a multiplet. But if I look at these two states I can obtain, you see that the free indices that I got, apart from this A and alpha and alpha dot, are A and A dot. Remember that I said when you have A and A dot, these are related to these are related to indices in the T4. And in fact, if you decompose, for example, a string which is polarized along the T4, you can use the representation theory of SO4 to decompose it exactly in something which has an index A and A dot. In the previous case, we had an index A dot to B dot, so that's related to tensor multiplets. But it's natural to consider that when you have something like this, just one leg along the T, once you reduce to 6 dimensions, this will be related to vector multiplets. So this will, upon dimensional reduction, the intuition is this should be described in 6-dimensional supergravity by vector multiplets. So the idea is that the CFT suggests that states like this, or states like this, should be described by linear excitations of your supergravity, which are captured by vector multiplets. In this talk in particular, I will focus on this state. The reason for that is that essentially it looks like the 0,0 states apart from this 1, 1. So it's the simplest one that you can think of. And apart from that, just personal intuition for this one was that the natural choice is, so when you have linear excitation, in principle, you can excite all the fields in ADS3 cross S3. So it could be also, you can also excite the metric. There's no reason that only the vector excitation is excited. But here in this case, both the left and the right sector are conspiring to get to give you a vector index. And in my intuition, this was the most natural state to consider that excites only the vector excitation. And once you start with this new lowest weight state for your bosonic, what you can do is you can act just with your symmetry generators and create a whole new slew of bosonic states, which you can backreact and generate new solutions. Okay, so these are states in the CFT. They should have counterparts in your supergravity picture. The question is, why bother with this? Why is this important? The first one is it has potential to give you new non-trivial solutions to supergravity, which is important in itself. The second one is its potential to generate new microstate geometries. And as Daniel was saying, it's kind of important to know what are the generalities of your potential microstate of black holes. What are the things that are specific for different microstates? So by fully backreacting these, you can find new playgrounds in which to probe black hole physics. Also, last year, when we were trying to figure out a resolution to a very specific degenerate limit in which microstate geometries develop an infinite throat and develop a horizon, it turned out that vector multiplets specific role and could potentially resolve this limit. So it had a very particular importance to find out whether you can create microstate geometries which preserve SO4 symmetry. So that was another motivation I want to look at this. And tying to what Stefano was saying in the previous talk, it will turn out that these solutions, when you uplift them to 6 dimensions, they can be described in a pure NSNS frame. And so they can potentially, if you remember the plot that was here, they can potentially serve as a non-trivial starting point for a worldsheet analysis, where you start your string perturbation theory and potential starting point for transitions between heavy geometries. Okay, so now that we have some motivation, let's try to actually construct these solutions, these perturbations. The summary of that is that CFT analysis suggests there should be vector perturbations within of ADS3 cross S3, which should be supersymmetric. And the idea is that I would like to construct a bulk which has the same properties as your CFT states. In particular, I know that there is a lowest weight state in my multiplet, which is, as the lowest weight states, it's annihilated by anything that lowers its SU2 eigenvalue or anything that lowers its SL2R eigenvalue, both in the left and right sector. And it turns out, and if I will assume that these properties do not change as I flow in the moduli space. And if I start with global ADS3 cross S3 with a particular radius where both the ADS3 and S3 radius are the same, I can make an ansatz based on the fact that this metric only depends on the r and theta coordinates. So all of the other dependence I put up in an exponential, and everything else I make an ansatz where I have a function multiplying a one form on the S3, and a function of ADS3 multiplying a form on S3, and a function on S3 multiplying a one form on ADS3. It turns out, and then the fact that I can explicitly construct the symmetry generators in the bulk description allows me to impose the same condition I had in the TFT state on my linear perturbation. And as it turns out, these conditions are, together with supersymmetry, are enough to completely constrain my linear perturbation and give it an explicit form like this. I have parameterized this perturbation by a small parameter b tilde, which will just give you the amplitude. So as long as beta tilde is small, this will be just a perturbation. If I start to increase, it will become, I will have to deform a geometry. I have hidden some details here. I have a coordinate transformation. Everything before that was in the NS sector of the theory. I've talked about the NS states in the NS sector. I've talked about the global ADS3 cross S3. In going to this slide, I've gone to the Ramon sector. So I've made a coordinate transformation. And from now on, I'll just talk about the Ramon sector. So this is just for the aficionados. So just to see what happens next. So this was just, and what can follow now, just generate more states by acting with supersymmetry, by symmetry generators. And I get the most general perturbation, which contains this factor, which contains, which is just a factor containing k, m, and n quantum numbers. And I get a phase which contains the V dependence. One thing that is important here, you might ask, why haven't we considered the vector multiplets when considering two charged microstates? And the reason for that is that these solutions start with n is equal to 1. So all of these perturbations are V dependent. And when you back react them, all of these solutions have momentum. So there are no non-trivial vector superstrata, which are two charged solutions. Okay. When b tilde is small, when the perturbation is small, obviously you solve linearized equation of supergravity. But when you want to solve the full Einstein equations. So how do you do that? If you want to solve the full Einstein equation, this is hopeless. It's really hard. Mathematica doesn't in a couple of days. But what you can do is you can use supersymmetry. Supersymmetry simplifies your equation. And in fact, what has been shown, impose supersymmetry, you can analyze your supersymmetric configurations, your BPS configurations, and you can decompose them in such a way that your equations of motion, your BPS equation, actually become linear and become upper triangular. So if you solve them in a very particular way, you're just basically solving Laplace equations. And so this is the BPS ansatz. So this contains all supersymmetric solutions, which contain a tensor and a vector multiplet, dimensional minimum gravity coupled to a vector multiplet. The only thing I need to do now is I have a metric, I have a free form, which is unconstrained. I have a two form, which is which contains the vector multiplet, and I have a dilaton. They're linear, yes. Yeah, this is what allows everything to work essentially, because then you can just add fluctuations. Okay, so the whole point of the supersymmetry is that it, instead of working in 6-dimensional supergravity, what you can actually show is that your V, and you can use the S1 circle, which is the common circle where the D1 and D5 branes are wrapped. You can actually kind of like take it away and everything in the 4-dimensional space. And as it will turn out, you can fix the metric on this 4-dimensional space. So what you end up solving is just electromagnetism in Euclidean flat space. This ansatz is not very important. What I've highlighted is that, you see, you decompose all of your fields in order, and what you're solving now is just basically the V and just some scalars, Z1, Z2, and ZA, and then some forms. Upsala. Okay. Yeah. Okay. Now the BPS equations are very difficult. I'm not going to show them in full detail. The only important thing is that they separate themselves into several layers. What happens is that you first solve for the metric, but that equations are very difficult, and it turns out that you can actually, in most of the solutions, you can fix them to be just a flat metric. And then the next layers correspond to the gauge fields. So in a principle, what you then solve is electromagnetism. And when you have just tensor fields, which was what the superstrata, the individual tensor fields didn't actually talk to each other. So what happened was that you can solve, for example, the B field and the B field decomposition, and then the C2 field decomposition has actually very similar solutions. Once you introduce one field, once you introduce a vector field, you break this democracy between tensor fields. So you introduce a very specific order in which you have to solve these BPS equations. And the order in which you solve them is essentially you start with one combination, θ1 and Z2, which is not that important here. But what essentially boils down to is a self-duality equation and then some Laplace equations. And you can think of this as sort of like electromagnetism, because the rate of change of Z2 kind of gives you the spatial the change of θ1. Once you have that, what I mean by linear is these solutions are, just to go what I mean by linear, you can see that θ1 and Z2 are completely linear in these differential equations. Once you solve this, once you have θ1 and Z2, for f tilde and omega f, this solution again becomes linear. And once you solve these, you feed them back into the second order equation, and these solutions for θ2 and Z1 are linear again. The way you can think about these kind of looping is to think about where the perturbation comes in. The perturbation in our case comes in at this order. Once you find the solution to these equations, you find the back reaction, which gives you a gauge field, and the back reaction of this gauge field then back reacts on the influences of how momentum and angular momentum in this geometry are distributed. So think about it's the BPS equation kind of equations introduce the physical, actually the interpretation of if you put more and more gauge fields into your system, they will essentially back react on your geometry, and they will change how much momentum and how much angular momentum you have. You can measure asymptotically. And just as a perhaps something that I haven't mentioned before, the momentum is captured by this curly F, and the angular momentum by this omega. Okay. How to write this perturbation? We saw that the perturbation can be written in this form. Now, the background can be rewritten, use a certain coordinate system, which is just the generalization of what you use for Kerr. So you have this sigma. The sigma is just, it's adapted to have a ring singularity. So you put your sources, you put your D1 and D5 branes sort of like on a singular circle, and then you can actually see that your perturbation is just a non-trivial profile along this circle. In a principle, if you remember what Stefano was saying when he was talking about supertube, this is exactly the round supertube profile on which you put a non-trivial vector field profile. And then, as I said before, as long as B tilde is small, this is a perturbative solution. But now, as I turn on B tilde to be large, if B similar to A, you get a non-trivial back reaction. And so now what happens is you have to solve for the third order and fourth order equations. This is the kind of a novelty compared to the original superstrata, where you basically have back reaction. So you only had to solve for momentum and angular momentum. Here you have to solve first the back solution for the gauge field, and only then you can solve for momentum and angular momentum. And this kind of gives you another complicated another layer of complications, and it means that you cannot. I haven't been able to find all of the solutions analytically in a closed form expression, even though its expression is a really very ugly sum. But nonetheless, I haven't been able to do so. What I will do now is I will focus on single mode solutions. As I said before, because the BPS equations are linear, you can an arbitrary linear combination of those is still an arbitrary linear combination of solution is still a solution, and then you can back up those, and then they interact non-trivially. But if you have just one mode, so if you have just one set of K, M, and N, what you can show that actually all the source terms which appear in higher layered equations are V independent. Now this is this sort of like a miracle, because in original superstrata, the fact that you had to cancel out V dependent terms was called confusion, and it was very important to avoid any potential singularity in your geometries. So, but in these solutions, there is no need for that. So now let's look at the beautiful mess that this is. If you look at the gauge field components, because you actually there is a of the two form, but actually a combination. Your fields already have some back reactions in them, and in terms that they solve almost every equation apart from the self-duality condition, where you find some source term, non-trivial source term, and if you stare at the equations long enough, you can make an ansatz, which essentially reduces to solving for two scalar coefficients f1 and f2. And because your background is just flat space, if you massage it long enough, what you can get is that you find the Laplacian equation for f2, which you can actually solve. The solution is not very nice. It's given in terms of a long-winded series of just basically, it's a, sorry, no, not series, a sum, which contains a lot of these delta functions, which I've flashed here before. So these are the building blocks of all the solutions. So the solutions in general don't look very nice, but you can actually obtain them analytically. Once you have f2, you can then plug them into a differential equation for f1, and you can find them analytically. The new thing here, okay, just to summarize, is once you have the perturbation, the first thing you need to do is you need to solve for the gauge field. Okay. Next thing, once you have the gauge field, then you can go and try to find the curly f and omega function, which contain the momentum and angular momentum. Turns out you can solve the momentum function relatively trivially, because it does not depend on any of the previous solutions. It's again goes down to just a simple Laplace equation, which you can again solve in terms of this f functions. But then equations for omega is slightly more complicated. And the reason for that is that because here it contains the solution to the previous equation. It's to the previous layer. And because the previous layer is given by an ever-increasing sum, the higher you go, the more and more source terms you have, and you cannot solve them. You cannot solve them, at least in a closed form expression. For example, if a different reason for that is that basically the source term in this case, it goes as has a really high singularity term, which is related to the fact that also omega mu can be slightly similar. That's fine because it doesn't spoil the metric. Okay, now this gives you a very systematic procedure how to solve these differential equations, but for general KMNN, this doesn't tell you anything important. Now let us see what the solution look like for a particular case. Yeah, of course. No, so the source term is 1 over sigma, sorry. The source term is 1 over sigma, but the sigma itself, sorry. The source term for this one is 1 over sigma. Okay. But what actually this means is this mu, this component is 1 over sigma, but actually in the metric it gets canceled out. So it's not just a component. It's an artifact of the fact that you split your metric into several components, but then when you look at the solutions, you actually there is a subtle cancellation imposed by regularity that ensures that your metric is smooth everywhere. Okay. So it's a valid question. It's a valid question, and this is. But usually, what was done before is that people were able to just isolate this term and just cancel it out. So you solve just regular equations, and then you knew what this singular term was. But here you just have to deal with it.
It's the sort of Faust. It's a typical thing that happens all the time with this kind of game. To linearize the system, you have to write the metric and all the fields in a rather strange-looking ansatz. And every piece of the ansatz typically has singularities. But when you assemble it all together again, the singularities all cancel out. But so the penalty you pay is that you have to deal with singular pieces, which then all cancel out. But the game is to get the linear system that you can solve.
Yeah.
In the simpler examples where you just have gravity and tensor multiplets, the structure of the linear equations is at, I think it's the second layer, is that you're solving some Laplace equation for the omega and f with sources that are quadratic in some previous step.
Yeah.
Okay. Now you have more, so you'll get some equations that say some amplitudes are quadratic in other amplitudes. So now you've got more layers. Does that proliferate, that you have some amplitudes that are now cubic and quartic and other things, or is the structure still that sort of the things that are new are still just quadratic in previous things?
In principle, it could be. But what happens in this case is that because the perturbation actually appears in layer 3 rather than layer 1, so layer 1 is still B0.
Yep.
And then the final layer where you calculate omega and f, it's always the combination of the first and the third layer that appears. So it's either you have source terms which are b times b, or b0 times b squared. So at least in this case, it doesn't proliferate. So you always, it's the perturbation series, perturbation expansion truncates at b squared, at least in this example. But in principle, you could have. If you had something, for example, which changes Z1 at the linear level, then in principle, you could go to infinity. But I think it's sort of like one of those kind of things where, because you're always, for example, because you multiply Z1 by theta 1, but Z1 is from the first layer and it doesn't change with B, and theta 1 is from the third layer, which goes as beta squared. This gives you beta squared. So, you just finished beta squared.
To put it in sort of more general terms, the origin of the quadratic on the right-hand side is because of Chern-Simons interaction. So you have D star F is F wedge F. I think if you had a more complicated Chern-Simons interaction, you could probably go to higher orders. Whether it would linearize or not, I don't know. But it's just the Chern-Simons interactions that giving the structure.
Okay. Any other questions, by the way? I have 20 more minutes. The similar solution looks like this. It's something only a mother could love, but at least a mother loves it. The one thing that is kind of miraculous in this kind of case is that the V dependence only comes in at the perturbation level. So this is the B to the power of 1 term. And this is the only v-dependent term. Everything else kind of cancels out. So in terms of coiffuring, all the quantities are self-coiffuring. So what you can see is that the solutions are really something which are just rational functions of A and R and theta. And they're slightly complicated, but not that much. I'm moving around. And no, so this is, I'm still in 6-dimensional supergravity. I'm still in 6-dimensional supergravity. And a non-trivial check that you can do is that once you backtrack these geometries, you can asymptotically, you can check, you can read out the momentum and angular momentum charges by just expanding the metric asymptotically. And what you find that there's, after you properly go quantize these charges, is that they match what you predict from the CFT. So that's a non-trivial, zero-order non-trivial check that your CFT states really match your yes.
Is your solution weakly curved for any B tilde?
Weakly curved. A weakly curve in terms of what? Yeah, it's smooth everywhere. It doesn't alpha prime doesn't even come here. So it's a purely supergravity solution. I think. You want to add something? No.
Just going to say it's typical in these things when you add momentum charge, the geometry gets big and fat, and there's never any failure of supergravity limits.
Yeah. So perhaps just as a comment on this, what you can show is that first of all, as we were talking before, as you decompose your BPS ansatz, you get individual terms which are potentially diverge. But once you reassemble the metric, you get that things are regular. But apart from that, you really need to impose one regularity conditions, which ensures that your circles at specific points, at potentially dangerous points, don't diverge. And this is the combination that you have to do. And this kind of resembles the strand budget relation that you find. Basically, this is the radius of ADS. This is related to the total number of charges that you have in your system. A is just related to the number of vacuum strands or plus strands that you had in your system. And this B, which is related to B tilde in this fashion, is related to the amount of new non-trivial states that you put into your system. It's related to the fact whether you get some divergences in your system. One can actually check what happens to the Y circle, what happens to the size of the Y circle. And in the log-log scale, what you can find is asymptotically, this is just increases linearly as it usually for ADS-free. And then somewhere in the middle with a scale which is set by B. So in this case, I've taken some particular values for B, and at this scale, this is approximately B. This value, the Y circle stabilizes, and you get a region which is actually ADS2 cross S1. So you get a finite length ADS2 horizon, which then again transitions into ADS3 region. So then it smoothly caps off. So again, this has the typical structure of a microstate geometry, ADS3 asymptotically. It has a finite size ADS2 horizon, which caps off instead of forming an extremal horizon, extremal finite size horizon as is usual for a black hole. Perhaps something that is slightly interesting that I didn't understand, or that I still don't understand, is if you look at your the back reaction involved also Z1 function, which is a harmonic function. It doesn't change. It gives you a V-independent perturbation. What you can show is if you take the supertube limit, which is the near source behavior, it actually decreases the amount of charge that you have. So decreases the amount of charge that you have for one value of n, but then increases the amount of charges you have for different values of n. So what happens is that it seems like this charge, this U1 charge that you have is sort of like dissolved in your geometry. And as you move further away from the source into asymptotically, you either pick up more U1 charge or you lose it. And the fact that you pick it up or lose it depends really on whether you have angular momentum or not angular momentum in your system, which is characterized by this factor of m. But the thing is, even if your charge decreases as you go towards the source, actually the regularity conditions that are flashed in the previous sites prevents it from ever becoming negative. These solutions are very nice to behave everywhere. So the difference is the value of m. On the left-hand side, you have 1, 0 n solutions, and on the right-hand side, you have 1, 1 m solution, 1, 1 n solutions. Okay. What I
the fact that the function z is growing.
Yeah.
That signifies normally you have z decaying at infinity like a 1 over r. So if I
okay, no. So this is normalized compared to z11. So
okay.
I've taken the r squared behavior out.
Okay.
Yeah. No. I've taken the r.
You don't have any negative charge or anything like that.
No. It's just like it's just comparative to the standard solution. You've taken some out. Everything still falls off at infinity as 1 over r squared. Okay. One of the main motivations, as I said, to study these vector multiplets is to see whether they would resolve a singular limit. Just as a recap of what a singular limit is, we have two parameters, or have several parameters in the solution, but one of the parameters is a. If you take a goes to 0, what happens is that actually you increase the length of the throat, and in doing so, you restore an SO4 rotational symmetry. So in a sense, this is the limit which is particularly important for your black hole systems because your microstate geometry becomes more and more similar to a black hole. But then we analyzed this kind of behavior and found a stringy solution which contains vector multiplets, which contains degrees of freedom carried by vector fields, which did not form this extremal horizon. And we wanted to see whether if you make the solution that we found from stringy analysis was actually still degenerate. So this is a non-degenerate solution, and I wanted to see whether if you take the a goes to 0 limit, you actually resolve the spherical symmetry and develop a non-degenerate horizon. And this is actually not the case. The problem still remains. If I take a to 0, your geometry just becomes that of a BTZ black hole. And that you can see here is by just if you fix r in terms of the radius of ADS, you just start to form a longer and longer throat until a goes to 0. And a goes to 0, basically you just get an infinite throat, and your geometry just becomes that of an extremal BTZ black hole. So this is a problem. Why? Because on the CFT side, taking 8 goes to 0 just corresponds to a pure state. So on the CFT, you have a pure state, and on the gravity side, you still have the degenerate solution, which has an infinite throat, and therefore non-zero entropy. So you have a geometry with a non-zero entropy dual to a pure state. Clearly, some new ideas are needed to resolve this, and this will be the topic of several talks this week, including Yishwan and Dimitrios, who will talk about this on Thursday and Friday. Okay. Before I finish the last couple of minutes, let me talk about going to 10 dimensions. So far, all I've done is solve differential equations in 6 dimensions. I've only solved equations of motion in 6 dimensions supergravity. The idea now is to go to 10 dimensions because then I can relate my sources of vector fields to some stringy sources. And one of the particularly nice frames that I can use is the frame where I have F1 and S5 P global charges, but then the vector fields are actually carried by D0, D4, or D2, D6 charges. And the reason for that is that in this frame, the internal symmetry of T4 is preserved. And one can actually make an ansatz for the metric and the form fields. I work in the democratic formalism, which I have also a 6 form and an 8 form field strength in type 2A. And what you can actually show is that by making this ansatz and a particular identification of fields, that your 10-dimensional equations of motion just reduce to the equations of motion that we solve in 6-dimensional supergravity. So what this allows you is what you show is that the solutions to the 6-dimensional equations of motion will then solve the 10-dimensional equations. And so you found a way of parametrizing your stringy sources. Then you can use all of the machinery of string theory to then use T and S dualities to transform between different frames. And in particular, so the first frame I can think of is the F1 and S5 system, in which I have a C1 field which contains these D0, D4 charges. And then I can interpret this, the 10-dimensional metric in string frame, the dilaton, and the B field. I can decompose them into quantities like this. And then I can say, well, in this case, the Z1, just from the metric and from the way the dilaton behaves, is just the fundamental string. The Z2 corresponds to the distribution of NS5s, and so on and so forth. The important thing here is that really what you can see is that ZA, which is just the DV component of your one form, corresponds to literally the point sources of D0, D4 branes in your R4. Why is this important in the grand scheme of things? The last thing that I'm going to say before I conclude is because you can do a series of S&T dualities in which you can show that these solutions can be recast in a purely NS frame. In particular, what you can show is that in this case, all of the new dipole carriers which give you the momentum are just contained within the Z9 component of one form which multiplies the Z9 component of the B2 field, and just a factor which multiplies the DZ9 component of the metric. And all of this, so basically this would mean that if you have a vector strata, you could potentially really start as a starting point for a potential string analysis. To do so, the only thing that you have to consider now is that the metric and the B field will be explicitly V-dependent, and they will involve a direction in the T4. And in fact, this is something that Sean and Shumanshu have been thinking about lately, especially the fact that how to involve the T4 direction. Okay. Summary. So what I've presented now is an algorithmic approach of how to construct asymptotically S3 cross S3 superstrata which have vector field excitations. I've proposed some states in the symmetric orbifold point which should correspond to these geometries, especially the geometry, and shown that some zero order that these proposal passes some zero order tests. And as Stefano was discussing before, this should complete the catalog of all back-reactive solutions which are based on orbifolded background. So now what is left is you need to start thinking about on the orbifolded ADS3 cross S3 or orbifolded supertube solutions, which, for example, Masaki has been thinking about lately. And what we found that these solutions, one of the unfortunately negative answers to the questions that I had for these solutions is such geometries are not enough to resolve the A goes to 0 limit. In fact, new ideas are needed for that. And we've also discussed several uplifts to 10-dimensional supergravities to propose possible stringy sources for the BPS ansatz, and in particular shown that there is an purely NS frame, which give new ideas of how to use these geometries. It's sort of like an what is there left to do? So all of these solutions were ADS3 cross S3, asymptotically ADS3 cross S3. Extending them to asymptotically flat solutions would be interesting because then you can possibly even get the linear dilaton region. Again, constructing new solutions based on orbifold backgrounds would be also interesting. As I said, there is a proposal for the CFT states. It will be interesting to make more stringent, more detailed holographic tests, whether this is actually the case. And because one of the frames in which you can describe these solutions is purely NSNS, this makes these backgrounds nice to study any stringy calculations in them, to perform any stringy calculations in them. In particular, what might be interesting is, which might be in general interested for this program, is how to probe transition between heavy states. So for example, we studied stringy infall into these solutions. As the string falls in, because of divergent tidal forces, the string gets excited, it gets massive, and then as the string would get trapped in the geometries, eventually it will back react and it will force a transition between a heavy to heavy state. perhaps this might be one of the backgrounds in which we do this. As I said before, one of the technical issues about these solutions is that you always solve a flat space solution. There are several perturbations of S3 which contain perturbations of the metric, but these are very hard to solve, but they're still unconstructed. So they are, apart from a paper by Bogdan, Anthony, and Nick, who solved it in the who provided some examples in the three-dimensional formulation. And also, it would be interesting to see whether one can do. I started this talk by talking about back reactions of trying to pump energy into systems. It would be interesting to see whether you can do this in also other asymptotic spacetimes. And I would just like to point out the recent paper by people in the house, who actually looked at 4-point correlation functions, and they found a way in which you can actually study correlation functions of heavy light-light correlators in the integrated correlator formalism. And this kind of resembles the idea where you increase the number of particles to get to a heavy state. Okay, this is it. Wine and cheese. Unless there are no questions. Unless there are questions.
Can you go back to slide number 26?
Yeah, sure.
How many S dualities have you applied in order to reach this duality frame from the original one?
2.
So it's still weakly coupled.
Yeah.
And I have a second.
No. So you take an S dual, then do a bunch of T dualities, and then an S dual.
And that.
D0, D4? No, D0, D4, D1, D5. Then you put several T dualities, and then you put an S dual.
Well, another question. You mentioned that in the limit of A goes to 0, the CFT state becomes pure. Can you explain this statement?
The CFT is, so the idea is that all of these solutions are dual to pure states. So even when A is not equal to 0, these are dual to pure states.
Okay.
So yeah, so there is no.
Can I ask a really basic question here? So so you have in this frame you have NS5 F1 P charges, but then you also have these F1 and P charges along the 9.
Dipoles, right? So
okay, so they are dipoles, even though they're not, because they wrap only 9.
Yeah. So basically, they have polarization along the 9. So only the first 3 should be thought about as global charges.
Okay, good.
The other one should be thought of like, you have your fundamental string, which you're allowed to oscillate in your 9th direction. So locally, you would have some charge pointing in the 9th. Sorry.
Which goes up at some other location, moving Y goes backwards.
So it has some. I mean, it's listed as 9, but it has some non-trivial profile
along Y,
making it a dipole.
No.
along Y. The profile is along Y.
No, so it wraps the Y direction, but it has polarization.
9.
Sorry.
The ZA, the F1.
ZA.
Yes, the ZA stuff.
F1 wraps 9.
It doesn't wrap 9. Nothing.
Well,
That's there.
That's what
No,
it says.
but it has polarization in the 9th direction. It has like, so it's like this, right? So.
No.
So you have the Y circle, right? And you have the 9th, and you have something like this.
Yes.
So you have the.
F1 along Y is the charge.
Yeah, is the
And
global
F1
charge.
along 9 is the dipole charge.
Yeah. So locally, you would have some charge along the Y direction, which points along the Y direction. So you have B. You have essentially it's this, right? So think about. So you have some ZA, which would be a V-dependent. So you have some B9 V field, but it's V-dependent. So when you integrate over V, it cancels out because it's so it's a dipole.
Okay.
But it has a non-trivial direction along the 9.
Okay, I see. So when you list it as 9, it's not that it wraps the 9 circle. It's that there's some profile in it.
Yeah. So only the first stop, perhaps I should say this. Only the first stop are global charges. Everything else is a dipole charge.
So just to understand the CFT dual states again that you had conjectured.
Yeah.
So you had written that as a G supercharge acting on a state with a fermionic excitation.
Yeah.
Does it
Yeah.
basically mean it's an alpha excitation?
And I don't think it's an alpha excitation in general. If it's multi-wound, it's not an alpha excitation. I think if k is greater than 1, it's the commutation. It's not a non-trivial commutator. I think it's a non-trivial anti-commutator.
But in terms of
But
the D's and
morally
alpha should be something, right?
It should be. It's morally speaking, I think it's the same. Yeah. It should be something like this.
Okay, that's very exciting. I always wanted to know what the dual of alphas were, and we could never find them. And the reason that's so exciting is that when you actually
Can you clarify that? Are they really alphas, or I thought they were just toroidal fermionic things, right?
So I think so. The idea is that basically you have that G, because G is alpha times
D. Yeah.
right. So so that would be. So G as the supersymmetry generator is an alpha, which is just an expansion of the bosonic field, and then multiplied by psi, which is expansion of the fermion field. But then when you act on an antichiral primary could have a psi already, like as a one thing. So you can anti-commute those, so it should be similar to. I think it's morally similar, but it might not be exactly the same. There might be some non-trivial commutation, non-trivial thing next to it.
So we've always been curious about that, because when you do this radiation from the J mart, so one particle goes out, that's the radiation, but the particle leaves behind has fermions which give angular momentum, but also has an alpha. But we could never compute that back reaction, so we couldn't see where it's going as it back reacts. But if you actually know what that looks like, then you would know something.
Yeah, no. So the idea was that that we wanted to. It should be morally similar to alpha, because it just has these. It has just an index similar to an alpha. But I wouldn't put my hands on it. There might be some non-trivial things which happen, especially if you have higher twist index. I think it might be if you act on just on. I think it's just on plus. It might become something like an alpha, but I had an argument for that, but I forgot it. I was thinking about it the last couple of days, but I forgot about it.
Okay, we can talk later about it.
More questions, comments? Well, I guess if not, then let's conclude with a big round of applause.